I told you in the last video that benzene is an example of an aromatic compound. And in this video, we'll talk through these 4 criteria to determine if a molecule is aromatic or not. And then we'll look through some examples and determine if they are aromatic. The first criteria, now this list you should write down in your notes because you'll use these in class. But the first criteria is to have a cyclic arrangement of unhybridized p orbitals. The first criteria is to have a cyclic arrangement of unhybridized p orbitals. So this tells us that we must have a cyclic compound. If you're looking at a molecule that doesn't have a ring, you can automatically tell that it's not going to be aromatic. It has to have a ring in the molecule. Within the ring, you also need that arrangement of p orbitals. So every atom, now criteria number 2, every atom of an aromatic ring, so all the atoms in the ring, must have an unhybridized p orbital. It can have substituents off the ring, and those substituents don't have an unhybridized p orbital, but within the ring, each atom must have that unhybridized p orbital. That's how we get, I'm going to scroll up real quick, that's how we end up with this molecular orbital with the p orbitals overlapping across all atoms in the ring, and that's a key feature of aromatic compounds. Criteria number 3, aromatic rings are planar. That happens when we have all sp2 or sp hybridized atoms. We'll mostly be looking at sp2. We have a planar molecule, so all aromatic rings are planar. And then the cyclic arrangement of p orbitals must contain 4n plus 2 pi electrons. So if you count up all the electrons that are in p orbitals, so the pi electrons in the aromatic ring, the number of them must be equal to 4n plus 2, where n is an integer. It can be 0, 1, 2, 3, and so on. This is called Huckel's 4n plus 2 rule. So when all 4 of these criteria are met, you have an aromatic compound. The electrons in the p orbitals can resonate across all of the p orbitals around the entire ring and can end up by going in one direction around the ring in the same spot that they started. So let's think about benzene. We know it's aromatic, but let's interrogate that a little further using these 4 criteria. If you haven't already, you should commit the name benzene to memory. The molecule benzene is a 6-membered ring with 3 pi bonds, and each bond alternates single and double within the ring. When we write benzene like this, we don't draw the implicit hydrogens, but you might remember that each carbon also has 1 hydrogen bonded to it. So the formula for benzene is C6H6. If we think about resonance within benzene, all of the pi bonds within the ring can resonate around to form, wherever there was a single bond, now we have a pi bond. And wherever there was a pi bond is now just a single bond. So benzene is drawn in these 2 formations most frequently. where we have the pi bonds in a different location, add in resonance brackets. And these two drawings or representations of benzene are equal energy. Doesn't matter really which way you draw it unless specific electrons are forming a bond in a specific location. We'll talk about that in the next unit. But we have this resonance. We can even continue resonating electrons around the ring. And that will end up, if we follow the green arrows, we essentially go back to that original structure. Make sure that's a resonance arrow. Okay, so let's look at our criteria. First, do we have a cyclic arrangement of unhybridized p orbitals? Yes, we know that about benzene. Every atom in the ring, does that have an unhybridized p orbital? Yes, every carbon atom has an unhybridized p orbital. That means every carbon atom is sp2 hybridized, so it is a planar molecule. And then the number of pi electrons. So we have 3 pi bonds, 2 electrons per pi bond. That means we have 6 pi electrons. And does this follow Huckel's rule? Really? Can we find an N such that we have 6 is equal to 4N plus 2? That works if N is equal to 1. So that means we follow Huckel's rule here. So we have a planar molecule. All carbons in the ring are sp2 hybridized, so each one has an unhybridized p orbital, and we have 4n plus 2 pi electrons where n is equal to 1. That means this is aromatic. Let's do another example. This is one we saw when we were working through the Diels-Alder reaction. So we'll do 1,3-cyclopentadiene. We have cyclopentene ring on carbon 1 and carbon 3. We have double bonds. So looking at criteria 1, do we have a cyclic arrangement of unhybridized p orbitals? We do have a ring, so we have a cyclic molecule, but if we label the hybridizations of each carbon atom, we have, I'll write sp2 in blue here. These carbons are sp2 hybridized. They have an unhybridized p orbital, but this carbon at the top is sp3 hybridized. So that means it does not have an unhybridized p orbital. I'm going to redraw the molecule and add in those p orbitals. I'm just going to use one color for now. Each of our sp2 carbons have an unhybridized p orbital, but the sp3 carbon, it doesn't. It has 2 bonds to hydrogens. So there's no unhybridized p orbital for the pi electrons to resonate around. So criteria 1 is not met. Criteria 2 is not met. It's also not planar. Criteria 3 is not met because sp3 geometry is tetrahedral, which is not planar. Remember, sp2 is trigonoplanar. So it's not a planar ring. And then we already know this is not aromatic, but for fun, let's count up the pi electrons. We have 2 pi bonds. That means we have a total of 4 pi electrons. Can we get 4 for our 4 pi electrons equal to 4n plus 2, with n being an integer? We can't. So these are not equal to each other. If n is 0, then we've got 4 equal to 2, which is not true. If n is 1, we would be writing 4 equal to 6, which is also not true. So this is not an aromatic. Now, you don't necessarily have to go through every single criteria every time. If you find one criteria that's not met, then it's not an aromatic compound. Here are a couple more examples to think about. I'll go through a little bit quicker. Toluene is a common benzene derivative with 1 methyl group bonded to the ring. Biphenyl is another molecule where we have 2 phenyl rings, which have the same bonding pattern as a benzene. These are bonded to each other. And then I don't have the name of this molecule on hand, but I can think about that one as well. In the first molecule, we see we have essentially a benzene ring. So I'm looking at toluene here. We have a benzene ring with a methyl substituent. We already know that the benzene ring on its own is aromatic, and the carbon atoms within the ring have not changed. Each one has an unhybridized p orbital, and we have 6 pi electrons. Each carbon within the ring is planar, so this one is aromatic. For biphenyl, we're looking at 2 versions of, for biphenyl, we're looking at essentially 2 benzene rings that are bonded together through a single bond. Within each ring, each carbon again has an unhybridized p orbital. So actually in this molecule, it's not an overall ring. So we actually have 2 aromatic rings in this molecule. We can say this is aromatic. The total number of pi electrons that are in each ring is 6. Same thing as toluene. We just have 2 of them, so each ring is aromatic. In this last example, we have a 3-membered ring and a carbon chain. Carbon chain has 2 double bonds. In this case, we can see immediately looking at, well, we need a ring. So we see there's a ring in the molecule. But each of the carbons in the ring are sp3 hybridized. So this one is not aromatic because we do not have that cyclic arrangement of unhybridized p orbitals. I want to do one more example of a heterocycle. So this means at least one atom is not a carbon. So here's an example molecule, furan. Where we have a 5-membered ring with 4 carbons and 1 oxygen atom. So is this molecule aromatic? It might be helpful to first consider resonance to think about whether pi electrons can resonate around the entire ring. And it's helpful to think about that because when we first look at the molecule, it might appear that we have 4 sp2 carbons and an sp3 oxygen. But that might not be the case if we consider resonance and whether that oxygen can create a double bond. So I'm going to erase these p orbitals. So let's start with the oxygen non-bonding electrons. Those can resonate to create a pi bond between the oxygen and a neighboring carbon. But then we have to resonate away some of the pi electrons from that neighboring pi bond, and then same thing with that last pi bond there. We can't create a pi bond right here because that would end up with too many electrons around that oxygen. So let's draw what this resonance structure looks like. So we have a new pi bond between oxygen and the carbon on the left, new pi bond across the carbon-to-carbon bond on the top, and then a non-bonding pair on the carbon. Now we have a positively charged oxygen and a negatively charged carbon. This is a valid resonance structure for this molecule. And so now I'll ask, what is the hybridization of oxygen in this second resonance structure? In this resonance structure, it has 3 electron-dense areas. That means this is an sp2 oxygen. We have an sp2 oxygen and sp2 carbons. So we do have a cyclic arrangement of unhybridized p orbitals. We can say every atom in the ring has an unhybridized p orbital. That means, and we said that each atom is sp2 hybridized, so it is planar. So let's now consider whether we have the right amount of pi electrons. We have 2 pi bonds. If we look at the original structure, there are 2 pi bonds. And we have 1 pair of non-bonding electrons that can resonate starting from the oxygen. So total, we have 2 electrons per pi bond, so that's 4 plus the 2 non-bonding electrons. That's 6 pi electrons in this ring that can resonate throughout the ring. We know from our benzene example, that having 6 pi electrons aligns with Huckel's rule, where that is 4n plus 2, where n is equal to 1. So we have the right number of pi electrons. So here we have an aromatic compound.